Good morning and welcome to the over 60 schools we've got joining us online from right around Australia today. My name is Pete and I'm a science communicator at Questacon, Australia's National Science and Technology Centre, and I'll be moderating the event for you today. Now, before we start, I'd just like us all to pause for a moment and think about the land that you're currently on. I'm here in Canberra on the land of the Ngunnawal people, who have been studying the stars for thousands of years. They are the first scientists, first astronomers, first innovators here in Australia. And so are the traditional custodians of the lands right around Australia where you're each joining from today. To all, I would like to acknowledge the elders past, present, and emerging from our First Nations who are here with us on these lands. Now, when we talk about space, it's important to pause and remember the legacy of our First Nations people, not only here in Australia, but around the world, that has helped to shape our knowledge and understanding of our universe. And this is particularly important when today we're chatting about NASA's Sounding Rockets program, which excitingly will be launching from here in Arnhem Land in Australia later in 2022. More on that soon. But before we get started, some housekeeping. We've got a fantastic lineup of guests for you here today. And if you have any questions that you would like to ask our experts, please use the Q&A box and the function at the bottom of your Zoom screen. It can also be found under the More tab. We have a team of Questacon staff who will be helping to moderate and filter the questions, and we'll do our very best to answer as many of these as possible in the designated time. So send your questions through at any point during the online broadcast. Now, of course, as a live broadcast event, there is the chance of some small technical problems. And in this case, if it happens, please bear with us because we're going to resolve them as quickly and smoothly as we can. So to officially start the proceedings today, it's my pleasure to welcome from the US Embassy here in Canberra, Natalia, who will be introducing the event and further welcoming our special guest presenters. Natalia, over to you.
Thank you so much. My name is Natalia Arenas, and I am the Science Technology Officer here at the US Embassy in Canberra. I am delighted to be here and bring together our team of NASA experts who will be talking about the Sounding Rockets campaign, which is really a great example of US-Australia collaboration in space. And the United States and Australia's partnership in science and technology really demonstrates why international cooperation is so essential for industries to thrive in a peaceful and purposeful manner. And our relationship of many years on space cooperation really embodies these shared values. When talking about the US-Australia space relationship, it's really impossible not to mention the first time that man landed on the moon back in 1969. I think back then we probably couldn't have comprehended where we would come today in space. And really that was just the beginning of US-Australia space exploration. But we haven't stopped there. The United States and Australia have a decades-long partnership right here hosting the Canberra Deep Space Communication Complex, also known as the Tidbinbilla Tracking Station. And in the Tidbinbilla Tracking Station, it's really one of NASA's largest space communication facilities outside of the United States. Our scientists and engineers work together at the tracking station to support communication for the landing of rovers on Mars, the arrival of New Horizons to Pluto, and the entry of Juno into orbit around Jupiter. And now coming back to the present in 2022, the Australian Space Agency recently announced plans to send an Australian-made rover to the moon as early as 2026. And this is all under a contract with NASA. And the rover is going to collect lunar soil to examine if it could support human life on the moon. And of course, what we're all here to learn about today, the NASA Sounding Rockets campaign. In Northern Territory, a team of NASA staff that you'll hear from today have been working with Equatorial Launch Australia and the Gumatj traditional owners on a project to send 3 rockets into orbit starting later this year. This is a momentous project as it will be NASA's first launch outside of a commercial facility from the United States, and it's happening right here in Australia. It's an example of our deep collaboration built from our mutual trust. And we may be the best partner for Australia in their aerospace industry, but it's clear that we can't do this without Australia, and Australia is just as crucial to the United States. And so for all of you listening today and thinking about exciting out of this world careers in space and futures in science and technology, you really should consider many of the exchange programs that the U.S. Embassy has to offer, including our Fulbright program and our International Visitor Leadership Program. But now for our big presentation today, I'm pleased to introduce Dr. Kevin Franz and Scott Bissett, our NASA team, who will talk about the Standing Rockets program. Over to you.
So I'm Scott Bissett. I'm the NASA campaign manager for our Australia 2022 campaign. I'm also the deputy chief of the Sounding Rockets program that is run out of NASA Wallops Flight Facility in Virginia. So really excited to be here talking to you today, talk a little bit about, what is the Sounding Rocket, what is the Sounding Rocket program, and what are we doing in Australia? So let me bring these slides up here and get started. So first off, what is a campaign manager? So anytime we take a sounding rocket to a remote location, it is considered a campaign. It could be one sounding rocket, up to 5 sounding rockets that we take out at any time. And I'm responsible for coordinating with all the various entities that we work with, the Australia Space Agency, our partners at Equatorial Launch Australia, the U.S. Embassy, as well as many other organizations
Scott,
back here.
Scott, sorry to interrupt. We're having some problems seeing your slideshow. If you've brought that up, could you please try bringing that up again?
I sure can. Give me 1 second here. Any better?
Perfect. Thank you, sir.
Okay, there we go. So I'm Scott Bissett. So my education, I got my BS in Industrial and Systems Engineering from Virginia Tech. Interesting, I've started as a mechanical engineer before making my change sophomore year. Just realized mechanical wasn't quite what I wanted to do, and transitioned to Industrial and Systems. Right out of school, and actually while I was in school, I got an internship at Wallops starting in 2005, and worked for 2 summers before coming full-time to NASA Wallops in 2007. I started out as a hardware and systems engineer before moving up to project management on the contractor side, and then in 2007 started my tenure as an actual NASA employee as an operations manager, and recently moved over to the deputy program management role. Some interesting facts about me. I've traveled to 8 different countries sporting sounding rockets, and within the last less than 10 years, I've traveled to Norway over a dozen times. So we do quite a bit of traveling. I really enjoy the outdoors, which makes the program a great fit for me. One thing I will say, obviously working in sounding rockets, there isn't really a educational path to take just to get into sounding rockets. It really is just all the different STEM subject areas and being a problem solver. We do employ aerospace engineers, mechanical techs, but really it's just having that problem solving ability that STEM gives you. So the NASA Sounding Rocket Program, or NSRP, at a glance. So what is a sounding rocket? They take their name from the nautical term to sound, which means to measure, and we're taking real-time measurements during the flight itself. All of our missions are suborbital, meaning we don't actually place anything into orbit. And we utilize an unguided and spin stabilized launch vehicle. We basically set the fins of the launch vehicle, which you'll see here in a minute, to an angle to induce a spin on it when it leaves the launch rail. We launch approximately 18 flights per year from all around the world. And at any given point, we can have 40 payloads or missions active at any stage, from kickoff, requirements development, all the way through actually conducting the launch operations. The different types of missions, I won't read through all of them, but basically we support all of NASA sciences, and we support our own technology development program to further the Sounding Rocket program, as well as educational opportunities for students. And what better way to see what a sounding rocket is than a quick video here. So let's see if this will play for you.
3, 2, 1, come on.
So this was a launch out of Wallops Flight Facility. It was a 2-stage, meaning 2-motor flight. So you see the first stage drop away, and there the second stage ignition there. The exact same launch vehicle is actually what we'll be using for our missions in Australia later this year. So the nature of the sounding rocket program. So, why are we here? Why do we have a sounding rocket program? It enables cutting edge science to be conducted, which you'll hear from Kevin here shortly. It enables instrument development for future orbital missions. Sounding rockets are much cheaper, much quicker than the larger orbital class missions. So it's an easy way to prove out technology. And we also do scientist development, which Kevin will talk a little bit about. So the characteristics, as I mentioned, we're part of NASA's Low Cost Access to Space, or LCAS program, and which is where we get the grants and work with the different universities for providing access to space. We rely on military surplus motors, which allows us to keep our costs down. Rocket motors are very expensive, but since we can get them surplus, it allows us to keep our costs low. But that does mean we accept higher technical risk by keeping our costs low. We don't necessarily use a flight qualified hardware, but we had that built into the program that we're willing to accept that risk. And we also use minimal project teams. A project team could be less than 10 people to see a mission through. And our program manages it from cradle to grave, from mission inception all the way through launch. You could have that same team all the way throughout the whole mission life cycle. And we support worldwide mobile operations, which I'll talk about in a minute. And it's implemented via our NASA contracts. We have a lot of contractors that work for us. And really the motto of our program is we go to where the science is. Not only, as we said, a sounding rocket to take the measurement in flight, but also around the world where the particular science is needed. Services provided. So I'm not going to read through that list there, but again, we manage everything from start to finish. A scientist will bring an instrument, or you'll hear me refer to it as a payload, which is really what we're trying to get up into space to take these particular measurements. They will bring it to us as the instrument, and we're responsible for integrating that into the sounding rocket. So we do everything from the design, the manufacturing. We have our own manufacturing facility, the integration, the testing, all the way through taking the mission to the field to do the flight itself. We also do all the flight performance and launch vehicle analysis and processing. So again, we hit basically every type of different engineering background that you can think of. We have mechanical engineers, software engineers, aeronautical engineers. We have mechanical techs, electrical techs. It really does cover the gamut. We have safety as well. So our launch vehicles, obviously all the science isn't the same. They don't need to get to the same apogee or altitude, the target area where they want to do their science. And obviously not all payloads or experiments are created the same. So when one is brought to us, we select the appropriate launch vehicle for hitting the particular science of interest, which you'll see on the next page exactly what I'm talking about. This chart here on the bottom, you can see the weight. I apologize, it is in pounds, not in kilograms. But the scientists will come to us with the payload weight and the approximate apogee, and you can see this is how we would go about selecting the particular launch vehicle in question. In this case, in the orange writing is the particular launch vehicle we're using. It's a Terrier Black Brant Mark 9 is what we refer to it as. And we're targeting around a 200 to 300 kilometer apogee for these particular telescopes. But don't be fooled about, it's a sounding rocket, it is smaller, but these have a lot of performance. You can see some of these higher performing vehicles that consist of 3 and 4 motors can get all the way up to 1,600 kilometers. And for a frame of reference, the International Space Station's at 400 kilometers. So we can get 4 times higher than that with a sounding rocket to take the particular measurements. And what does a payload consist of, or a sounding rocket consist of? I talked about the 2 motors there. The 2 motors are the images you can see with the fins that actually induce the spin on the rocket to keep it stable. And then moving down to the payload itself, it's really all the different subsystems that comprise the smarts of a sounding rocket. The forward section there is a parachute recovery. We don't fly those on all missions, but for these particular missions in Australia, we do have a payload recovery system on board. The telescopes are very expensive to build. They take a long time to build. We like to get them back in one piece. There's an attitude control system. So this actually allows us to point the telescope or science instrument at a particular target real time. So not only can we pre-program pointing, but we have the ability, if we see something and we're not quite on target, to real time uplink a command and point the telescope. The telemetry section provides the data. So all the images that a telescope's taking, all the science we're gathering, that's what links it back down to Earth real time. We do very little onboard recording. Most all the data we get is live back down to the ground. And then the experiment section, which Kevin will talk about, that houses the various types of instruments that we can support. And last is the shutter door, and that's what protects the optical end of the telescope and will open up once we get out of the Earth's atmosphere to actually view the particular targets. And worldwide operations. So we go all over the world. As I said, wherever the science is. There's 2 remote launch sites in Norway that we routinely launch from. We launch rockets out of Kwajalein Atoll, which is in the Marshall Islands. Australia, going to Equatorial Launch Australia, located in Nhulunbuy in the Northern Territory later this year. We have a launch site at Wallops Island where our program is actually located. We do launches out of White Sands Missile Range in New Mexico, as well as in Poca Flats, Alaska. In fact, we have a team about to start a countdown the next 15 minutes for a launch out of there. And so why go to Australia, you ask? So we have a very long history of launching out of Australia to give astronomers access to the southern hemisphere sky. You know, there are just targets we cannot see from the northern hemisphere, and it has to be done for the southern hemisphere. The last time, unfortunately, we were able to do that was in 1995 when we launched out of Woomera Test Range. So we're very excited to be getting back to Australia to do this critical science to NASA. And why the Northern Territory? Why Equatorial Launch Australia? As I mentioned, we want to get these telescopes back. So we're looking for a land-based range so we can actually, bring these payloads back down to land them under parachute to recover them and reuse them in the future. We are targeting a mid-2020 window for 3, again, Black Brant 9s. Those are the missions right there. It's our mission number, along with the scientist or the principal investigator, along with the name of the experiment itself. As Natalia mentioned, this is the first ever launch from an international commercial range for NASA, not just sounding rockets, but NASA at large. So it took a lot of work to get here. So we're very excited to be back and really appreciate all the cooperation and collaboration with Australia to make this campaign a reality. Again, it's being conducted from the Equatorial Launch Australia's Arnhem Space Center in Nhulunbuy in the Northern Territory, a brand new launch site that we're excited to be launching from. We did complete an 8-week setup trip in September to October of 2021. We had a team of about 30 people out there. This was setting up all the infrastructure needed to launch rockets, and I'll show you a couple pictures here. And then for the campaign itself, we have a team of about 80 traveling out. I mentioned small teams, but for a remote campaign such as this, it takes a larger team, and we have 3 missions, so the teams are a little bit larger, and there's 3 of them. And last, obviously, as I mentioned, we're performing recovery of the payload and the spent motor cases. The goal is to have a clean range, so we pick up everything that we are actually launching. 2 quick plots just to show you, give you an idea of what the missions in Australia will actually look like. So the plot on the left is the time versus altitude that we're targeting. So again, around the 250-kilometer altitude for these particular telescopes. And then downrange, how far, what distance are we going to cover during the launch? And in this particular case, around 200 to 250 kilometers for these missions. And a few pictures of the work we've done thus far. So that top middle picture is the team out there in the Northern Territory, and that is a NASA-owned launcher that we brought in and set up. That's a picture you can see on the lower right there. So you can see it takes a lot of manpower and equipment to get this set up. And then the bottom left picture is all the mobile ground assets we need to actually download the telemetry to send commands to point the telescope. The power in the US is different than Australia, so we do power conversion. So again, electrical engineering, power, we sort of touch it all. And so to close, before I hand it over to Kevin, one more slow motion video of a launch out of Wallops itself. So there's a styrofoam cocoon around this particular payload so we can control the environment around it prior to launch. We can be sitting out in the heat and or cold depending on the launch site, and we want to maintain a certain temperature prior to launch. And so this is a 3-stage vehicle. So you'll see the first set of fins coming up here. That first stage is a Black Brant. One of the stages we'll be using in Australia. followed by a second stage Terrier, and the third and final stage that will obliterate the Styrofoam, a Taurus, or Terrier, sorry. And with that, I'll close out my presentation and hand it over to Kevin. This is just for everyone's knowledge, that's our mission patch that we actually have, which we don't always do for our campaigns, but in this particular case, it's one of significance important to the program. So we actually have a mission patch with the 3 missions there that you see in our multiple partners. And with that, let me see if I can stop sharing my screen and hand it back to Kevin.
All right. Thank you, Scott. Good morning, everybody. I'm Kevin France from the University of Colorado. So I'm a professor at the University of Colorado, as well as NASA's campaign scientist for our trip to Australia in the next couple of months. I'm also the principal investigator of one of the 3 science missions that's going to fly from the Northern Territories. So on a personal note, I've been working on getting science launches from somewhere in Australia for over 10 years now. So we're really excited about being able to come down to do this science, and are really delighted to see all of the STEM education interest in this project. And I hope that that we can continue this discussion, going forward, but also when we get there. So let me cue up my slides here. Okay. Great. So so I'm going to focus primarily on my my rocket payload, our experiment, but I'm going to touch a little bit on the science that we're doing, why we need to be in the Southern Hemisphere and in Australia to do this, and then some of the, not just the science, but also the technology development we do as part of the program, as well as the mentoring and student training. So this is a still shot of one of our engineering flights for the same payload that we're going to take to the Northern Territories. And just like Scott said, this is a 2-stage motor. So in this time-lapse movie, or time-lapse image, you see the first stage here at the bottom, and then it burns up, falls off, and then about 6 seconds later, the second stage fires, and then that's what takes us up to above 250 kilometers, where we do our science above Earth's atmosphere. So just a little background about me. So I have degrees in astronomy and physics. I am terrible at math, but I thought physics was interesting. And if I went to college and stuck with it, I was sure I would find something that physics was applicable to. And so I happened to take an astronomy class when I went to college, and I fell in love with it. And even though I found physics very challenging, I was told that if I stuck it out, that I would get to do astronomy for my job, which seemed kind of crazy at the time, but I've been able to do that, and it's been very gratifying. So I've been working on rockets since I was an undergraduate at Boston University. I started working on rockets in 1998. So that's me in 2001, recovering a rocket from White Sands Missile Range. It's part of my PhD dissertation. So I've been doing this in various facets for a long time now. What I'm really interested in are planets around other stars, extrasolar planets in the search for life outside of the solar system. And that's what 2 of our 3 rockets are going to be working on this in a couple of months. So I also, do some other things outside of work. And then I was also, I don't usually say this until I meet a graduate student, but I was a member of the world's greatest astronomical rock band. So with some of these things in mind, my parents were concerned that I would never amount to anything. But today I'm happy that I actually get to talk about things as exciting as the search for life around planets outside the solar system. So let me show you a little video that gives you the context of what we're looking for with extrasolar planets. So when we search for signs of life, we look for an environment that's similar to ours. So that means we look for stars that are like our sun, and we look for rocky planets where we can have liquid water. And we call that the habitable zone. You might have heard this also referred to as the Goldilocks zone. And so those are our 4 rocky planets in the inner solar system. But the habitable zone is really an energy balance between the energy from the parent star and the planets. So it depends on what type of star you're around, where your habitable zone or where your Goldilocks zone is. If, for instance, Earth was around a hotter, more massive star, like here at the top, our habitable zone would move out because the star was putting off more energy. And then if we were around a cooler star, like a red dwarf star, the habitable zone would move inward. So this is just one way that the star really determines how we find and where we search for the signs of life. Now, on Christmas Day, all right, so I think I've said this already. On Christmas Day, we launched the James Webb Space Telescope, and this is, you might have seen some of the really cool early press release images from James Webb. And one of James Webb's primary science goals over the course of its 5 to 10-year life is the search for habitable environments. And so James Webb will be out there starting in the summer of 2022, or northern summer of 2022, this investigation for the signs of life on planets outside of our solar system. Now, of course, just like here on Earth, our relationship with the sun is critically important. And the same thing is true on extrasolar planets. If the star sends a prohibitively large amount of X-rays or high energy particles, it could disrupt the balance that we experience here on Earth, and it might make certain types of planetary systems uninhabitable or bad places to look for life. So the big question that we're trying to answer with 2 of our missions are, how does the parent star change the planet? And to do this, we study the star because we have this beautiful James Webb Space Telescope that's going to go out and work on the planets. But sounding rockets and sounding rocket experiments have a unique role to play with going out and measuring the properties of the star and understanding how they affect habitability. So this is just sort of another blow up of a stellar flare where the star is belching off these huge amounts of charged particles, which zoom towards Earth and cause space weather. They also change the chemical composition of Earth's atmosphere, and that's how we look for life outside the solar system. So what I'm showing over here on the lower right is a spectrum in the infrared wavelengths of our 3 sort of biggest rocky planets in the solar system, Earth, Venus, and Mars. And you can see a couple of qualitative similarities. They all have CO2 or carbon dioxide features in their spectra because we all have CO2 in our atmospheres. But only Earth also has this strong ozone feature, or oxygen 3, this O3. And this is because Earth has an oxygen-rich, habitable atmosphere. So understanding which planets have these oxygen-rich atmospheres and how those oxygen-rich atmospheres interact with the star is really one of the key goals for astronomy over the next 20 years or so. And we're working with that now to understand which types of stars are most conducive to forming these habitable environments like we have here on Earth. So what are we actually going to do? So the cysteine-induced missions, those are 2 of the missions Scott mentioned earlier. They are going to study our nearest solar type neighbor. That's our nearest star that's just like the sun. That's Alpha Centauri. It's probably going to be our best place to look for a true Earth-Sun analog in the near future. And it's in the southern hemisphere sky. So if we can't observe from the southern hemisphere, we can't observe our nearest, our best opportunity to study a sun-like star. So we have these 2 missions, Deuce and Cysteine, that are going to go down and observe the Alpha Centauri system in ways that have never been observed before, even with the Hubble Space Telescope. So how do we do this? Well, we build telescope payloads. Here's a kind of the cartoon version of what one of the telescope payloads will look like. It's what we call a Cassegrain telescope. And so that means the light comes in, bounces off a primary mirror, and then bounces off a secondary mirror, and then comes to a focus somewhere behind the telescope. And that's exactly how the Cysteine payload works. I'll show you a picture of Cysteine in a second. But we add one more thing to it, which is something we call a spectrograph. And that takes the focused light from the telescope and breaks it into its constituent colors. And by studying the light and dark patterns in those spectra, we're able to understand how hot the star is, how fast motions are on the atmosphere of the star, what it's made of, And so it's basically taking the information that we get from a picture and multiplying its usefulness by some enormous amount. Okay, so this is what our cartoon version of cysteine looks like. Over here in the lower left is a drawing of cysteine. So again, you see a primary mirror, a secondary mirror, and then the spectrograph sits behind the telescope. And then shown below that is what the actual optics drawings of the actual optics look like when they're in the rocket scan. And then over here on the lower right, that's actually the cysteine telescope from one of our engineering flights, where you're looking down into the telescope and you can see the large primary mirror, the reflection in the large primary mirror behind there. So this is one of the payloads that we're going to be taking to the Arnhem Space Center. So not only are we going to be doing this science, but all of these payloads that are going to be launching this summer also are doing technology development that are supporting future NASA space missions. So I'll focus on what we do in cysteine. So cysteine is testing out a new type of telescope optic that we want to use on NASA's Super Hubble Space Telescope mission that we want to launch in the 2030s. And so what I'm showing here are two at the lower left. This is one of our optics that was created at the NASA's Jet Propulsion Lab. And then a second optic, this larger primary mirror optic that was created at NASA's Goddard Space Flight Center. And these are completely experimental. And so what NASA likes to do is invest a small amount of money into sounding rocket payloads where we can take this technology from basically the back of an envelope calculation, build small prototype versions of these instruments, fly them on sounding rockets to basically demonstrate that they can make measurements in space before NASA invests many, many millions of dollars in building a large instrument for one of these big missions. So again, all of the missions that we're talking about today do this technology development for NASA. And the last thing I want to talk about is kind of the steps we go through to get to the launch pad. So again, this is from one of the engineering flights of cysteine. I'm showing over here on the right, this is called a vibration test. Essentially, we take the rocket and sit it on an enormous amplifier. It's essentially a really big speaker. And we vibrate it with the same intensity that it would experience during launch. And we test it before we vibrate it, and then we shake it really, really, really hard. It's a very stressful thing to watch, something you've built for 2.5 years being shaken so loud you can hear it rattle. And then we test it again afterwards and make sure that it still works. And if everything goes okay, we get to run through the rest of the tests and take the payload out to the launch rail. And this is will look similar to what Scott showed in his slides. And again, we're flying on a 2-stage Terrier Black Brant stack up. And just like in the other one, just like in the video Scott showed, we are in this styrofoam box to keep us at a nice comfortable 25 degrees C, because that's where our optics like to operate. And then something that just to emphasize, when we do these campaigns, there's a tremendous amount of staff, not just the folks that are coming from the US, but all of our local collaborators and partners. And it really it takes a tremendous number of people to pull one of these flights off, much less 3. So this kind of brings us to the student training aspect and the professional development side of what we do on the science side of sounding rockets. So this is kind of the third leg of the stool. This is one of the unique programs that NASA offers, where a student can come in and get experience in all aspects of a NASA mission, a full spaceflight mission, from the development all the way through to building and testing, launching it, and then doing the science afterwards. And it all kind of fits roughly in the timeline of an undergraduate's 4 years or a graduate student's PhD dissertation. Along the way, you learn electrical engineering, mechanical engineering, more engineering than you ever wanted to know when things break. And you also get to work with the leading experts in these science fields. So it's a really fantastic program. And I'll just end by highlighting, these are the 3 principal investigators that have contributed to the Colorado payloads that we're sending down to Australia. And these are all students or postdocs or early career engineers that have contributed to these missions. So the impact of training these students up and then sending them on to work both in public and private space industry is what keeps it fun for me. And so we're really delighted to be able to do this science and bring this program to Australia this summer. So thanks for your attention. We'd be glad to take questions.
And thank you very much, Scott and Kevin, for that fantastic presentation. On behalf of everyone here at Questacon and the many schools around Australia, it's been really informative and thoroughly engaging. And as we mentioned, there is the opportunity to ask questions of both Scott and Kevin via the Q&A chat function. We have lots and lots of questions coming in from schools everywhere. And I just can't resist but kicking off by asking, Kevin, when's the band next playing? And will you be dressed as Power Rangers?
It's been a long time since the band, everybody grew up and moved to their respective places, and then COVID. But I'm hoping, if we can bring everybody together in Nhulunbuy this summer, I might fly everybody in.
That'd be terrific. Make sure you broadcast that one. I think we'd all like to tune in. Just one intriguing thought I had, when you send up a sounding rocket with the payload, is there traditionally only one experimental program associated with each payload, or do you sometimes load multiple into any one mission?
I guess I'll start by saying I'll let Kevin talk about the telescopes, but the different sciences we do support, you could have multiple universities with multiple instruments. The telescope is one big instrument, but some of our geospace missions we launch elsewhere, you could have a dozen or so instruments from different universities on board. And not only that, but you could launch more than one rocket at a time. We launch what we call a salvo, where we could have 2, 3, 5 vehicles in the air at once to do the particular science.
Yes, I agree. We fly these astronomical telescope payloads are large because our things are so far away that they're faint. So we tend to take up the whole rocket. But we sometimes will fly secondary payloads that will maybe be, say, looking out the side of the rocket during the flight to do secondary science. So there's a lot of opportunities for small instruments and small investigator teams to get involved.
And you both also mentioned the importance of retrieving and, trying to recycle and reuse the components of the payload and the systems that you test. When you fire the sounding rockets off, how can you predict and how do you know where they will land? And how, for example, within Australia, will you be aiming to retrieve them?
Sure. So we have, I guess, multiple ways of tracking the sounding rocket. So for the particular ones for Australia, within the telemetry system, we actually have embedded GPS. So the same thing you have on your phone in your car, we have on the rocket to tell us right where it's at. We also use radar, which is doesn't require a GPS satellite uplink to tell us where it's at. So we will track those all the way down to where they'll actually land. We also do a lot of analysis on the front end to predict exactly where they will go. So we have good control over where they're heading. And we actually, one of the things we do is measure winds real time leading up to launch. So we have a weather tower that measures the surface winds, and we launch weather balloons leading up to launch to measure the winds and correct for those winds. Now, recovery, how we're planning to do that, we'll actually be utilizing some local helicopters to fly out. We'll know where the payload landed. We'll do a search pattern to find it, land, go in, and that's where our partners at ELA and their partnership with the Gumatch and the others, to be able to get access to the land is extremely important to us.
I've got a question here, and it's come from Bianca. What are the impacts of the rockets returning to the land and to Earth? Is there any environmental impact involved there?
There's minimal impact, and actually part of our recovery plan, we do what we call remediation. Some things will land harder than others and could leave. To give you an idea of the size of the instrument itself, the radius of the diameter of most of our missions are 17 1/4 inches.
It's
but,
about 45
so they're not-
centimeters, 50 centimeters. Yeah.
There you go. Yeah. But we'll go out, and that's part of our recovery plan is to do that remediation. You know, if we have disturbed the ground at all, you know, we fill it back in and take care of local vegetation. But in terms of, I'll say, hazards, there are no environmental impacts though.
And you spoke of bringing out a lot of the team from NASA for the launch itself. There's a question here asking how many Australian scientists are involved in these missions, if any.
I can certainly speak to the Colorado teams, and yes, we have multiple Australian scientists involved. In fact, one of the original partnerships that we started with the exoplanet group here were people who were studying from the Anglo-Australian telescope, who were finding these planets that we are now interested in following up with James Webb and understanding their stars. So I can't quite speak to the team from the University of Wisconsin, but I know there are at least two university professors on each of the other two teams.
And a question from Mel, has there ever been a failed launch?
Yes, there has. There are different types of failures, unfortunately. So I mentioned, you know, we're lower cost, but we accept higher technical risk. It doesn't mean we're unsafe, but there is a chance of failure. And actually, our metric is 85% success, and we are a successful program. But a failure can be anything from a problem we've had in the not too distant past. It's called combustion instability. Basically, the rocket shakes a lot more than you want it to, and it breaks stuff on board. So it's not that the vehicle itself fails, but it breaks your instruments on board. You don't get the reading, the science you want. So yes, there are failures, but all of our safety planning is sort of done around those. We analyze all the different failure modes to be sure we're prepared for them.
And I saw a question here from, let's see, Lachlan. Exactly what direction will the rockets be launching? Is it absolutely vertical, or do you angle them slightly depending on the intent of the mission?
You want to go, Kevin, or you want me?
Yeah, sure. Yeah, so we do. We launch between 83 and 87 degrees. So do just a little bit off of straight up. But they go further up than they do horizontally. So, yes, but they're slightly tilted.
A question from Jane: will the launch be visible from Nhulunbuy, which is about 200 kilometers from Arnhem Land and the launch site?
From Nhulunbuy, absolutely. So we're actually one of the products that our public affairs office will put out is a viewing map. We do that for all the launches here at Wallops. You know, about the distance away you can see it and at what time. These are all night launches, which makes it a little bit easier to see as well. You know, you'll see the fire coming out the back end. But beyond Nhulunbuy, I couldn't tell you how far right now you'll be able to see it, but certainly even from town, like I said, being 15 kilometers or so away, they'll be able to see it.
And there's certainly a couple of questions from schools. Is it possible for schools to get access anywhere near the site to be able to watch or witness the launch event?
To some degree, yes. You know, there are safety areas that we have to keep people out of, obviously. And that's something we're working closely with our partners at ELA, the Space Agency, the Northern Territory government to sort of manage. You know, one of our goals while we're out there is to do outreach, you know, STEM events and things like this. So we're hoping there'll be opportunities, you know, leading up to launch to come out and see some of the, you know, the hardware and then the launch itself.
And a question from Bianca: have the Indigenous people of Arnhem Land been involved in the project, and what consultation took place?
Or ELA could give you much better, but yeah, they've been consulting, you know, with the Gumatj, the Northern Land Council, for years. I think we did our first site visit out there in 2016, and conversations were even happening now. We're consulting with them, and ELA is doing it on our behalf for the recovery portion of it. So yes, that's something we've taken very seriously. We actually had a welcome event during the site setup where we got to meet a lot of the local folks, and same thing, we're doing a lot of outreach there as well.
Some of the schools are asking where can they get more information about some of the training programs and the study options, which Natalia was mentioning earlier. Would either of you be able to speak to that, or should we get Natalia back in?
Natalia can probably give you the best answer. I don't know if Kevin can give you anything. We do student admissions. There are some, but they're through university grants. So it's not, NASA has its own internship program, but there are a lot more opportunities external to NASA itself.
Certainly what we can do is we can get some more information and include that up on the Questacon website and some of the links which might be on our YouTube channel. So we'll be able to put that information up there and get that and move forward. And from Kelkarinji School, what will happen and what would the rocket experience as it travels into space?
I'll take this one because it's our experiments that that both bear the brunt of the extreme force after launch, but also then enjoy that period of free fall or weightlessness where we take the measurements. So it's like we talked about, it's a two-stage launch vehicle. So you get two really big kicks, and when that's happening, your experiment will experience upwards of 12 Gs, so 12 times the force of gravity that we experience. And that is much bigger than what you would see on the space shuttle or really any large commercial launch vehicle. So they go fast and they leave the pad and are gone very, very quickly. And so you have to build your instrument to be able to withstand these tremendous forces, but then still make extremely precise measurements. So the Sistine payload will be measuring things at the arc-second level, and that is 1/3600th of a degree on the sky. So it's a real engineering and design challenge to be able to build something that will still make a precise measurement after it's been shaken that hard. But then as it goes up, as Scott mentioned, the shutter door opens and the telescope points at the celestial target we observe. Then before we come back into the atmosphere, the shutter door closes again, so we don't bring a bunch of superheated gas down with us. And the telescope, or the whole payload, begins to roll up as it goes into the atmosphere to distribute heat. The parachute comes out, and then it takes maybe about 5 minutes maybe 6 or 7 minutes after the parachute deployment for it to land, where we will eventually go pick it up. So it's a very exciting, and one thing I got to tell you too is that the students drive the rocket during the flight. So we have a command system. It's kind of like a $2.5 million video game, where the students are actually watching the video feed come down in real time and are pressing buttons that are controlling little gas jets on the rocket and steering the rocket around to make the observation in real time. So it will make your life at least 5 years shorter from doing it, but it's really exciting and a really great thing way that students basically take ownership of these types of projects.
I have to say, a very good friend of mine would give his teeth to be pressing those buttons and being able to steer that. I like the analogy to the video game too. We've got a very kind of big picture question here for you both. And what will happen if and when we find life or signs of life on other planets?
Great question. This question of are we alone in the universe is maybe the oldest philosophical question, and so I think for me it's interesting because it frames Earth's place in the cosmos. We're just one planet in one solar system among many, many, many solar systems, and or maybe we're unique. Maybe there aren't a lot of other Earths out there, but I have this desire to know this, and this is one of these things when I go around and give talks, that you start talking about, are we alone, and everybody in the audience starts nodding their head, and so, you know, I can't really speak to how how the world responds at large, but I think understanding our place in the universe is just one of those big questions that's worth pursuing.
I think certainly with space and astronomy, it's just endless, and the questions that provokes are just amazing. So there's a lot of wonder and excitement still to come, I think, in the discovery that we're yet to make beyond our own solar system, especially. I'd just like to thank you both sincerely for this fantastic opportunity today. It's been absolutely marvelous. And we've been talking a lot about NASA and the NASA Sounding Rockets program here in Australia. But of course, we also in recent years have established our own Australian Space Agency. And we're very lucky today to have Brenan Drew join us from the Australian Space Discovery Centre in Adelaide. Brenan, would you like to talk to us about some potential STEM careers and opportunities in the space industry in Australia?
Yes, absolutely. Thanks for the introduction, and hello from Arnhem Land in South Australia. I think my job here actually today was made very easy by Scott and Kevin, the previous speakers. They've given a very good overview of some of the science that we can get out of these space technologies and payloads that we're putting into space, as well as the sort of supply chain of rocket launches that are required to get there. And as both of them quite nicely indicated, that there's such a sort of gravity of people around them, 80 people in one of the teams to get the NASA sounding rockets here. So there's a great big workforce there. And just to highlight a few more other things on this example before I talk on some other things, there's greater teams in there as well. So I briefly mentioned environmental impacts are a study that happens. There's also a lot of legal matters that have to be considered with the Returns and Launches Act. There's a lot of communication, there's marketing, there's PR. So there's so many different aspects to these jobs or to getting these things out into space. I think my job at the Australian Space Discovery Centre is very exciting because on the one side, there's this greatly expanding space industry and the return of sounding rockets to Australia from NASA sounding rockets since 1995 is a really exciting example of that. So as this industry expands, there needs to be a growing workforce. And then on the other side, there are these STEM-capable learning secondary students, tertiary students. We've encountered primary school students who can name all the planets, all the dwarf planets, a lot of the moons of Jupiter, and some really great astronomical things like that. And there's a link between the two that we need the people to be STEM trained to be able to get us into space and to do a lot more things. And the Australian Space Agency has put together a civil space strategy. This outlines our goal to bring 20,000 more jobs to the space sector by the end of the decade. And as highlighted by the previous speakers, a lot of these jobs are engineers, the flight directors, the ones who initiate the launch sequences. A lot of the really hard, I think, STEM capable people will be able to tackle those jobs. There is a future where we need Australian astronauts, but we also need space tradies, not only to provide these launch license facilities, but if we want to become a space traveling society, we will need space plumbers, space builders, space electricians. To borrow from a statement from one of my work colleagues, Sam Nishke, he says that in the future, every job you could ever think of could be made so much cooler by adding the word space in front. So if you're interested in medicine or being a physician, why not be a space doctor? If you're a farmer, you can get into space agriculture, which might be viewing things from the sky or how we start to grow things on another planet. I read recently about a space poet and the Dear Moon mission, which is one that's going to take artists around the moon for inspiration, is another sort of trip into the humanities. So I think the possibilities are endless. And to give a little plug of my own, I never really knew what I wanted to do when I was going through school or university. I actually studied Egyptology for a decade, but now find myself in the space industry. Pathways can be very unique, and I think that as we get more into space and start sending more things to space and more people to space, returning to the moon, there's some very exciting jobs that are happening. One quick final thought before I turn back to questions, if there are any. The NASA Sounding Rockets program is a great one that does bring this attention to Australia. But currently there are Australian companies building rockets that will be able to take things to a space. There are Australian companies building satellite constellation systems. And we're really, for a space agency being only started in 2018, the Australian space industry is really punching above its weights in our niche areas. So come and join us, come and work in space. We want to do a lot.
I think the opportunities you've raised there are fantastic, and particularly that exciting thought of putting the word space in front of any career you can think of, and it suddenly becomes a lot more exciting. Just quickly, there's a couple of questions here, Brenan. What work experience opportunities are there for students here in Australia?
This is a great question, and this is something that we're starting to see more and more in university and even TAFE courses as well, about work integrated learning. So by undertaking your study or your certificate or your course, you're actually getting an insight into the space industry that can lead to a job in the future. So it's something that the pathway from study or from interest into the industry is one that is getting a lot of attention at the moment. And I would recommend talking to us, to the agency, to your local universities or TAFE. These pathways are coming, and these internships or work experience placements are a great way to get hands-on skills.
And one other question here, what subjects do I need to be good at, and what should I be looking at doing at university to work in a facility like NASA here in Australia or with the Australian Space Agency?
I think the exciting thing here is that it's extremely broad. Obviously, there's the science, the maths that are the foundation of many of these engineering pathways and engineering futures. But as I mentioned, there's people on our team who are space lawyers, who are space doctors. So my advice would be to follow your passion. Think about planting the seed of a space something, a space cleaner, a space builder. All of these possibilities will be there in the future. And if you're driven by passion, I think you will succeed.
Wonderful. Thanks so much for that short insight, but some really valuable information there, Brenan. And certainly for anyone who gets the opportunity to visit the Australian Space Discovery Centre there in Adelaide, it is a fantastic facility and well worth the visit. So thanks for your time this morning, Brenan. To all of the schools who have participated, thank you so much for your wonderful questions that you've been sending through. We will endeavour to provide some more information, answer some of those questions if we can, and get the answers back to you. And also for all the schools who registered for this broadcast, we have some additional information that Brenan has provided on space careers in Australia that we'll send a copy of to each school or a link to those programs. On behalf of Questacon, I would certainly like to thank our very special guests, Natalia from the US Embassy, Kevin and Scott from NASA and for Colorado University for their presentations, and Brenan over there at the Australian Space Discovery Centre in Adelaide. Thank you everyone for participating in this program, and I hope you found it as exciting and enjoyable as we have. Have a good morning. Thank you.